Chapter 6 of Ian Stewart's Nature's Numbers. The Broken Symmetry. Something in the human mind is attracted to symmetry. Symmetry appears to our visual sense and thereby plays a role in our sense of beauty. However, perfect symmetry is repetitive and predictable, and our minds also like surprises, so we often consider imperfect symmetry to be more beautiful than exact mathematical symmetry. Nature, too, seems to be attracted to symmetry, for many of the most striking patterns in the natural world are symmetric, and nature also seems to be dissatisfied with too much symmetry, for nearly all the symmetric patterns in nature are less symmetric than the causes that give rise to them. Great physicist Pierre Curie, who with his wife Marie discovered radioactivity, stated that the general principle that effects are as symmetric as their causes. However, the world is full of effects that are not as symmetric as their causes, and the reason for this is a phenomenon known as spontaneous symmetry breaking. Symmetry is a mathematical concept as well as an aesthetic one, and it allows us to classify different types of regular pattern and distinguish between them. Symmetry breaking is a more dynamic idea describing changes in pattern. Before we can understand where nature's patterns come from and how they can change, we must find a language in which to describe what they are. What is symmetry? The human body is bilaterally symmetric, meaning that its left half is near enough the same as its right half. As noted, the bilateral symmetry of the human form is only approximate. The heart is not central, nor are the two sides of the face identical. But the overall form is very close to one that has perfect symmetry, and in order to describe the mathematics of symmetry, we can imagine an idealized human figure whose left side is exactly the same as its right side. But exactly the same? Not entirely. The two sides of the figure occupy different regions of space. Moreover, the left side is a reversal of the right, its mirror image. As soon as we use words like image, we're already thinking of how one shape corresponds to the other, of how you might move one shape to bring it into coincidence with the other. Bilateral symmetry means that if you reflect the left half in a mirror, then you obtain the right half. Reflection is a mathematical concept, but it is not a shape, a number, or a formula. It is a transformation that is a rule for moving things around. There are many different kinds of symmetry. The most important ones are reflections, rotations, and translations, or less formally, flip turns and slides. To rotate an object in the plane, you choose a point called the center and turn the object about that center as a wheel turns about its hub. The number of degrees through which you turn the object determines the size of the rotation. For example, imagine a flower with 4 identical equally spaced petals. If you rotate the flower 90 degrees, it looks exactly the same, so the transformation, rotate through a right angle, is a symmetry of the flower. Rotations can occur in 3-dimensional space too, but now you have to choose a line, the axis, and spins object on that axis as the earth spins on its axis. Again, you can rotate objects through different angles about the same axis. Figure 1. Where is the mirror? Given an object and a mirror image of that object, choose any point of that object and the corresponding point of the image. Join them by a line. The mirror must be at right angles to the midpoint of that line. Translations are transformations that slide objects along without rotating them. Think of a tiled bathroom wall. If you take a tile and slide it horizontally just the right distance, it will fit on the top of neighboring tile. The distance is the width of a tile. If you slide it 2 widths of a tile, or 3, or any whole number, it also fits the pattern. The same is true if you slide it in a vertical direction, or even if you use a combination of horizontal and vertical slides. In fact, you can do more than just sliding one tile. You can slide the entire pattern of tiles. Again, the pattern fits neatly on the top of its original position only when you use a combination of horizontal and vertical slides through distances that are whole number multiples of the width of a tile. Rotation captures symmetry in which the same units repeat around circles like the petals of a flower. Translation captures symmetries in which units are repeated like a regular array of tiles. The bee's honeycomb with its hexagonal tiles is an excellent naturally occurring example. Where do the symmetries of natural patterns come from? Think of a still pond, so flat that it can be thought of as a mathematical plane and large enough that it might as well be a plane for all that the edges matter. Toss a pebble into the pond. You see patterns, ripple, circular waves, swimmingly moving outward away from the point of impact of the pebble. Ripples in a pond are examples of broken symmetry. An ideal mathematical plane has a huge amount of symmetry. Every part of it is identical to every other part. You can translate the plane through any distance in any direction, rotate it through any angle about any center, reflect it in any mirror line, and it still looks exactly the same. No translations, no other rotations, no other reflections. The pebble breaks the symmetry of the plane, in the sense that after the pebble has disturbed the pond, many of its symmetries are lost, but not all, and that's why we see a pattern. However, none of this is surprising because of the pebble. In fact, since the impact of the pebble creates a special point different from all the others, the symmetries of the ripples are exactly what you would expect. They are precisely the symmetries that do not move that special point. So the symmetry of the pond is not spontaneously broken when the ripples appear, because you can detect the stones that causes the translational symmetries to be lost.
You would be more surprised, a lot more surprised, if a perfectly flat pond suddenly developed a series of concentric circular ripples without there being any obvious cause. You would imagine that perhaps a fish beneath the surface had starved it, or that something had fallen in and you had not seen it because it was moving too fast. So strong is the ingrained assumption that patterns must have evident causes that when in 1958 the Russian chemist P.P. Belousov discovered a chemical reaction that spontaneously formed patterns. Apparently, out of nothing, his colleagues refused to believe him. They assumed that he had made a mistake. They didn't bother checking his work. He was so obviously wrong that checking his work would be a waste of time. Jack Cohen and the American mathematical biologist Arthur Winfrey, and the experiment is now so simple that it can be done by anyone with access to the necessary chemicals. These are slightly esoteric, but there are only 4 of them. In the absence of the appropriate apparatus, I'll tell you what happens if you do the experiment. This uniformity is not surprising. After all, you blended the liquids. Then you notice a few tiny blue spots appearing, and that is a surprise. They spread, forming circular blue discs. Inside each disc, a red spot appears, turning the disc into a blue ring with a red center. Both the blue ring and the red disc grow, and when the red disc gets big enough, a blue spot appears inside it. The process continues, forming an ever-growing series of its target patterns, concentric rings of red and blue. An infinitesimal cause produces a large-scale effect, and that effect is a symmetric pattern. Nature's symmetries can be found on every scale, from the structures of subatomic particles to that of the entire universe. Viruses are often symmetric too, the commonest shapes being helices and icosahedrons. The helix is the form of the influenza virus, for instance. Nature prefers the icosahedron above all other viral forms. Examples include herpes, chickenpox, human wart, canin infectious hepatitis, and many others. Volcanoes are conical, stars are spherical, galaxies are spiral or elliptical. According to some cosmologists, the universe itself resembles nothing so much as a gigantic expanding ball. Any understanding of nature must include an understanding of these prevalent patterns. It must explain why they are so common and why many different aspects of nature show the same patterns.
This is all very well, but it produces a deep paradox. If the laws of physics are the same at all places and at all times, why is there any interesting structure in the universe at all? Should that be homogeneous and changeless? If every place in the universe were interchangeable with every other place, then all places would be indistinguishable, and the same would hold for all times. But they are not. The problem is, if anything, made worse by the cosmological theory that the universe began as a single point, which exploded from nothingness billions of years ago in the Big Bang. At the instant of the universe formation, all places and all times were not only indistinguishable, but identical. So why are they different now? The answer is the failure of Curious principle, noted at the start of this chapter. Unless that principle is hedged around with some very subtle caveats about arbitrarily tiny causes. It offers a misleading intuition about how a symmetric system should behave. Its prediction that adult frogs should be bilaterally symmetric, because embryonic frogs are bilaterally symmetric, and according to Curious principle, the symmetry cannot change, appears at first sight to be a great success. But the same argument applied at the spherical bastula stage predicts with equal force that an adult frog should be a sphere. A much better principle is the exact opposite, the principle of spontaneous symmetry breaking. Symmetric causes often produce less symmetric effects. The evolving universe can break the initial symmetries of the Big Bang. The spherical bastula can develop into the bilateral frog. The 252 perfectly interchangeable units of the adenovirus can arrange themselves into icosahedron, an arrangement in which some units will occupy special places, such as corners. A set of 27 perfectly ordinary microtubules can get together to create a centriole. Fine, but why patterns? Why not a structureless mess, in which all symmetries are broken? One of the strongest threads that runs through every study ever made of symmetry breaking is that the mathematics does not work this way. Symmetries break reluctantly. There is so much symmetry lying around in our mass-produced universe that there is seldom a good reason to break all of it. So rather, a lot of survives. Even those symmetries that do get broken are still present, in a sense, but now as potential rather than actual form. For example, when the 252 units of the adenovirus began to link up, any one of them could have ended up in a particular corner. In that sense, they are interchangeable, but only one of them actually does end up there, and in that sense that symmetry is broken. They are no longer fully interchangeable, but some of the symmetry remains and we see an icosahedron. In this view, the symmetries we observe in nature are broken traces of the grand, universal symmetries of our mass-produced universe. Potentially, the universe could exist in any of a huge symmetric system of possible states, but actually it must select one of them. In so doing, it must trade some of its actual symmetry for an observable potential symmetry, but some of the actual symmetry may remain, and when it does, we observe a pattern. Most of nature's symmetric patterns arise out of some version of this general mechanism. In a negative sort of way, this rehabilitates Curious principle. If we permit tiny asymmetric disturbances which can trigger instability of the fully symmetric state, then our mathematical system is no longer perfectly symmetric. But the important point is that the tiniest departure from symmetry in the cause can lead to a total loss of symmetry in the resulting effect, and there are always tiny departures. That makes Curious principle useless for the prediction of symmetries. It is much more informative to model a real system after one which perfectly symmetry, but to remember that such model has many possible states, only one of which will be realized in practice. Small disturbances cause the real system to select states from the range available to the idealized perfect system. Today, this approach to the behavior of symmetric systems provides one of the main sources of understanding of the general principles of pattern formation. In particular, the mathematics of symmetry breaking unifies what at first sight appeared to be very disparate phenomena. For example, think about the patterns in sand dunes. The desert can be modeled as flat plain of sandy particles. The wind can be modeled as a fluid flowing across the plain. By thinking about the symmetries of such a system and how they can break, many of the observed patterns of dunes can be deduced. For example, suppose the wind blows steadily in a fixed direction, so that the whole system is invariant under translations parallel to the wind. One way to break these translational symmetries is to create a periodic pattern of parallel stripes at right angles to the wind direction. But this is the pattern that geologists call transverse dunes. If the pattern also becomes periodic in a direction along the stripes, then more symmetry breaks, and the wavy barkanite ridges appear, and so on. However, the mathematical principles of symmetry breaking do not just work for sand dunes. They work for any system with the same symmetries, anything that flows across a planar surface, creating patterns. You can apply the same basic model to a muddy river flowing across a coastal plain and depositing sediment, or the waters of a shallow sea that ebb and flow across the seabed phenomena, important in geology. Because millions of years later, the patterns that result have been frozen into the rock that the sandy seabed and the muddy delta became. The list of patterns is identical to that for dunes. Or the fluid might be a liquid crystal, as found in digital watch displays, which consists of a lot of long thin molecules that arrange themselves in patterns under the influence of a magnetic or electric field. Again, you find the same patterns. Or there might not be a fluid at all. Maybe what moves is a chemical, diffusing through tissue and laying down genetic instructions for patterns on the skin of a developing animal. Now, the analog of transverse dunes is the stripes of a tiger or a zebra, and that of a barachanoid ridges is the spots of a leopard or a hyena. The same abstract mathematics, different physical and biological realizations. Mathematics is the ultimate in technology transfer, but with mental technology, ways of thinking being transferred rather than machines. This universality of symmetry breaking explains why living systems and non-living ones have many patterns in common. Life itself is a process of symmetry creation of replication. The universe of biology is just as mass-produced as the universe of physics, and the organic world therefore exhibits many of the patterns found in the inorganic world. The most obvious symmetries of living organisms are those of formed icosahedral viruses, the spiral shell of nautilus, the helical horns of gazelles, the remarkable rotational symmetries of starfish and jellyfish and flowers. But symmetries in the living world go beyond form into behavior and not just the symmetric rhythms of locomotion. The territories of fish in Lake Huron are arranged just like the cells in a honeycomb, and for the same reasons. Territories like the bee grubs cannot all be in the same place, which is what perfect symmetry would imply. Instead, they pack themselves as tightly as they can without one being different from another. And the behavioral constraint by itself produces a hexagonally symmetric tiling. And that resembles yet another striking instance of mathematical technology transfer. For the same symmetry breaking mechanism arranges the atoms of a crystal into a regular lattice, a physical process that ultimately supports Kepler's theory of the snowflake. One of the more puzzling types of symmetry in nature is mirror symmetry. Symmetry with respect to a reflection. Mirror symmetries of three-dimensional objects cannot be realized by turning the objects in space. A left shoe cannot be turned into a right shoe by rotating it. However, the laws of physics are very nearly mirror symmetric, the exceptions being certain interaction of subatomic particles. As a result, any molecule that is not mirror symmetric potentially exists in two different forms, left and right-handed, and so to speak. On Earth, life has selected a particular molecular handedness. For example, for amino acids, where does this particular handedness of terrestrial life come from? It could have been just an accident or an evil chance propagated by the mass production techniques of replication. If so, we might imagine that on some distant planet, creatures exist whose moleculars are mirror images of ours. On the other hand, there may be a deep reason for life everywhere to choose the same direction. Physicists currently recognize four fundamental forces in nature: gravity, electromagnetism, and the strong and weak nuclear interaction. It is known that the weak force violates mirror symmetry. That is, it behaves differently in left or right-handed versions of the same physical problem. As the Austrian-born physicist Wolfgang Pauli put it, the Lord is a weak left-hander. One remarkable consequence of this violation of mirror symmetry is the fact that the energy levels of molecules and that of their mirror images are not exactly equal. The effect is extremely small. The difference in energy levels between one particular amino acids and its mirror image is roughly 1 part in 1017. This may seem very tiny, but we saw that symmetry breaking requires only a very tiny disturbance. In general, lower energy forms of molecules should be favored in nature. For this amino acid, it can be calculated that with 98% probability the lower energy form will become a dominant within a period of about 100,000 years. And indeed, the version of this amino acid which is found in living organisms is the lower energy one. In Chapter 5, the curious symmetry of Maxwell's equation relating electricity and magnetism. Roughly speaking, if you interchange all the symbols for the electric field with those for the magnetic field, you recreate the same equations. This symmetry lies behind Maxwell's unification of electrical and magnetic forces into a single electromagnetic force. There is an analogous symmetry, though an imperfect one, in the equations for the four basic forces of nature, suggesting an even greater unification, that all four forces are different aspects of the same thing. Physicists have already achieved a unification of the weak and electromagnetic forces. According to current theories, all four fundamental forces should become unified, that is, symmetrically related at the very high energy levels prevailing in the early universe. This symmetry of the early universe is broken in our own universe. In short, there is an ideal mathematical universe in which all of the fundamental forces are related in a perfectly symmetric manner, but we don't live in it. That means that our universe could have been different. It could have been any of the other universes that potentially could arise by breaking symmetry in a different way. That's quite a thought. But there is even more intriguing. The same basic method of pattern formation, the same mechanism of symmetry breaking in a mass-produced universe, governs the cosmos, the atoms, and us.